Hi class, welcome to our 2.2 Part 2 video notes, which will be continuing our learning of derivative rules. We're adding 3 new ones today, the derivatives of sine, cosine, and then one of the exponential functions. We're going to add more exponential function rules later on in this chapter. So let's go ahead and start with sine and cosine. So what I want to do in this video is just give you a little background of where we get the derivative for sine from. And then once I show you where we get it from, you can just sort of memorize it from there. But I want to kind of go through the formal limit process of finding the derivative of sine to show you that the formula or the rule really is true. So I'm going to use this setup. This is using the limit process for finding a derivative. Maybe I'll kind of give you a reminder over here. So the general rule for using, or not rule, but the general method for finding a derivative using a limit would be to set it up in this format, where you have the change in y over the change in x. So f of x plus delta x minus f of x all over delta x. And actually you could think of that as x plus delta x minus x, because that's really what that is. Because if you take x plus delta x and subtract x, well, all you're left with is delta x, right? So what is that? That's change in y over change in x between two generic x and y points on a graph. So maybe if we're thinking of it in terms of sine, which we are kind of in this case, so sine kind of goes like that and so on. So let's say we're trying to find the slope of the line tangent right here. We can think of that as x. And so what we do is we kind of move a little bit to the right. So I'm going to zoom in so you can kind of see. We go just like a little teeny bit to the right. We think of this as x plus delta x, because that little change between them is delta x, the change between these two generic x's. Well, then that point on the curve would generate a new y value, which we'll think of as f of x plus delta x. And then this y value here was f of x. So in this limit formula, what we're doing is we're just subtracting those two y values, f of x plus delta x minus f of x, and what that gives us is the rise, the rise of the slope of the line connecting these 2 points. And then when we do x plus delta x minus x, we're just finding the distance between these two x's. So we're finding the run, right? So this is like rise over run. And what that's finding is the slope of the line that connects those 2 points. But then as we let delta x approach 0, which is what this is doing, then this delta x, this change between x and x plus delta x, is going to 0. So this point is actually getting closer to x, and then this point on the graph is getting closer to this one, and then eventually we get the slope of the line just at that one point. We get f prime of x, the instantaneous rate of change of the function at the original x in question. And when I use this limit process with just x plugged in, which I am here, then this is finding basically the slope of any tangent line along the curve at any x value, because these are just generic x's and generic change in x's. So this is finding the derivative basically as a function of x, all of the different slopes of all the different tangent lines at any generic x. So that's the process I'm going to use here, and it will help us find the exact derivative of sine. Okay, so here's the expression I get when I plug in sine for f of x. I get sine of x plus delta x minus sine of x all over delta x. And I can't really simplify that right now, but what I can use is a sum identity. So we can think of that as sine of alpha plus beta, or sometimes it's a plus b. I'm not sure how it was done in your pre-calc class, but at any rate, this is where you have to use an identity to figure out what sine of alpha plus beta is. And the identity says it's sine alpha cosine beta. So you take sine of the first angle times cosine of the second one, and then plus cosine of the first angle times sine of the second one. So that's what sine of x plus delta x will turn into. So that'll be our next line. So now I have the limit as delta x approaches 0 of sine of x. So in this case, alpha is like our x, and then beta is like our delta x. So I have sine of x times cosine of delta x, and then plus cosine of x times sine of delta x. So that's what this first part equals. I still have to subtract sine x, and then all of that is over delta x. Okay, so now I'm here. So now I'm going to get kind of clever in how I choose to associate these together. So remember, addition is associative. You can associate whatever 2 things or 3 things or 4 things you want together in any way. And you can think of this as all addition, because I can think of this as plus negative sign. So maybe that'll help us with that. So then I'm going to regroup the numerator. So I'm taking the limit as delta x goes to 0, and I'm going to do sine x times cosine of delta x. And I'll just add over the negative sine x first. So kind of have like these, and then I'll add this term last. So I'm just kind of reassociating them, but that's okay. Addition's associative, so that's allowed. Okay, so then I get limit as delta x approaches 0. And then I'm going to factor out a sine from this first part. And so I get cosine of delta x minus 1 plus cosine x sine delta x in the numerator. And that's all over delta x. So now what I'm going to do is kind of split up the fraction, because there's a common denominator of delta x. I'm going to do the limit as delta x approaches 0, and I'll kind of do this part first. So sine x times cosine of delta x minus 1 all over delta x. And then I'll go ahead and add that second part, cosine x times sine of delta x all over delta x, because since they have a common denominator, you can write each part, like each of this part and that part, over that common denominator. And then I get the limit as delta x approaches 0 of, and how, this is how I'm going to kind of think of this. I'm going to think of it as sine of x, maybe you can think of that as over 1, and then times cosine delta x minus 1 over delta x, because that's kind of what I have here, plus, and then I'll think of this as sort of cosine x off on its own. You can think of it as over 1, and then times sine x over sine of delta x over delta x. So then what I'm going to use here is a couple different properties of limits, because we have this whole thing I'm taking the limit of, but in that I have like a product here, a product there, and then a sum. And according to the properties of limits, I can go ahead and find the limit of each of these things separately, and then multiply them, and then add them afterward. So that's what I'll do. I'll take the limit of each part separately. Well, if the limit is with respect to delta x, then it doesn't really have any effect on x, right? Delta x was a different value. It was the change between x and x plus delta x. So it's not affecting x at all. So the limit as delta x approaches 0 of sine x is just sine x. It didn't really change with the limit because it's x, not delta x. Whereas the limit as delta x approaches 0 of this part, cosine delta x minus 1 over delta x, that's one of our special trig limits that we had learned back in chapter 1. This was a special limit, and if you remember, it equaled 0. So that all goes to 0 when delta x goes to 0. And then I'm adding the limit as delta x approaches 0 of cosine of x, but again, it's of x, not delta x. So the fact that delta x is approaching 0 doesn't affect x. So then that's just cosine of x, doesn't change. And then times the limit as delta x approaches 0 of sine of delta x over delta x, which again is another one of our special limits. This limit here approached 1 as delta x approaches 0. So that just turns into 1. So then at the end of this, sine of x times 0 just goes to 0, and then I just add that to cosine of x times 1. So then that is my derivative of sine. The derivative of sine is actually cosine of x. cosine of x is actually telling us the instantaneous rate of change for all the points on sine of x with respect to x. So I actually ended up taking up a lot more space than I had originally intended. So I think I'm going to erase some of this and put our formula up here. So our derivative for sine, our derivative formula for sine, and this is the part that I want you to use from now on, is cosine. So now that you have seen the limit process worked out, I want you to write this down, make a big deal of it, and remember it. Because from now on, when we take derivatives of sine, you have to remember, okay, it's cosine, positive cosine. So that's our first new derivative rule for this video. Now I'm going to have to make some room to find the second one. Okay, so now that we've cleared some space, we're going to go ahead and do the same process with cosine. We're going to take the limit as delta x approaches 0 of, but now we're plugging in cosine as f of x. So it'll be cosine of x plus delta x minus cosine of x all over delta x, using our limit definition. So for this, we also need to remember the sum identity for cosine, which was this, cosine of alpha plus beta. So this was a little bit, cosines was always a little bit weird. So it's cosine alpha cosine beta, so cosine cosine, and then you do the opposite sign, minus sine alpha sine beta. So instead of alternating the function, it just changes the sign. So cosine alpha cosine beta minus sine alpha sine beta. So that is what I will do for my next line. So I have limit as delta x approaches 0. So I will rewrite cosine x plus delta x as cosine of x times cosine of delta x minus, because I do opposite sign, sine of x times sine of delta x. Because remember, x is like the alpha and then delta x is like the beta. But that's just this first part. I still have to subtract away cosine, and then all of that is over delta x. So then I am going to, again, like I did last time, I'm going to group things in a way where I put the cosine of x's together, because you can, addition is associative. It follows the associative property, so you can associate whatever you want in any order. Because you can think of this as plus negative cosine and plus negative sine x sine delta x. So maybe I'll write it that way. So you can see we're really just adding in any order. So then I have sine x times sine delta x. So I just basically added the negative cosine first before adding the negative sine x and sine delta x. And then all of that is over delta x. Maybe I'll go this way. So I'll take a limit as delta x approaches 0 of, and I'm going to factor cosine out. So I'll take the cosine of x out of this group, and I'm left with cosine delta x minus 1. And then all of that, well, I'll go to the next part, sorry. And then now I have plus negative sine x times sine of delta x. And then all of that is over delta x. Okay, then I'll swing that around to here. So from here, we're going all the way over to here. Limit as delta x approaches 0. And now what I'm going to do is split these two over the same denominator. So I have cosine x times cosine delta x minus 1 all over the denominator of delta x, plus, because what's going on there is I have like this part adding that part, and so since they're over a common denominator, you can add them separately as long as you keep them over the common denominator. So I have negative sine x times sine of delta x all over delta x. And then what I'm doing here is finding the limit of all of this. But you can see that I have multiplication going on, I've got addition going on, and then again multiplication. So the properties of limits basically say you can do the limits of all of those things separately and then multiply and add them at the end. So that's kind of what we're going to do, but we're going to think of it as, so this is equal to limit as delta x approaches 0 of, we're going to think of it as cosine x over 1 times cosine of delta x minus 1 over delta x, because that's really what this is. you could let cosine kind of be its own factor and then just multiply it to all of this. Cosine delta x minus 1 over delta x plus negative sine over 1. You could think of it that way and kind of think of it as being negative sine as its own thing times sine of delta x over delta x. And so since the limit is with respect to delta x, it's not going to have any effect on just the plain x's. It only affects the delta x's. So if I take the limit as delta x approaches 0 of cosine, well, that's just going to equal cosine. It's going to have no effect on cosine. And then the derivative of cosine of delta x minus 1 over delta x as delta x approaches 0, that's our special trig limit again, which equals 0. And then for the second part, so derivative as delta x approaches 0 of negative sine x, again, that has no effect on negative sine x because this is with respect to x, not delta x, so it just stays itself. And then the limit as delta x approaches 0 of sine of delta x over delta x, that's another one of our special trig limits. And so that will just equal 1. So then my final answer, so cosine x times 0, that just goes to 0, and I'm left with negative sine of x. So that ends up being the derivative for cosine. That's the rate of change. The instantaneous rate of change of cosine with respect to x is negative sine, is the derivative of cosine. So with the last one, I'm going to have to erase this a little bit and write the formula down so that you can remember it. But this here was the process we used to find it. So we know that this is legit. This really is the derivative for cosine. So let me make some space for it. So the derivative with respect to x of cosine of x for all x would be negative sine of x. So from now on, you don't have to go through that complicated process we just did. You need to memorize this formula and just use it because we know this to be true because we just found it, so we don't have to do it over and over again. Kind of like with the power rule and all those other things. Once we've proved it once with our formal limit, then we don't need to prove it every time. We can just use the rule. Okay, so that's our second rule for the video. Now for the third rule, I'm actually not going to go ahead and I'm not going to derive it for you, but I will tell you if you are interested in seeing how it's derived. You can find that on page 140 in your textbook. For this video, I'm just going to tell you what it is. And so this is the third function. So we're only doing the function y equals e to the x. We're not doing other exponential functions in this video, but that is coming later. But get this, the derivative with respect to x of e to the x is equal to, drumroll please, e to the x. It is literally the easiest derivative you will ever find. Remember it forever, okay? It is its own derivative. This is my favorite function. My favorito, okay? My favorite. Because the slope, right? Remember the derivative is the slope of the tangent line, right? The slope of the tangent line is equal to the y coordinate, right? Because e to the x would be the y value. So like if you take a point on the graph of e to the x, the y coordinate at that point would also equal the slope of the tangent line at that point. They're the same. It's the same thing. It grows at a rate of change. Like, okay, how do I say this? It grows as fast as whatever its y value is. If its y value is 100, it's growing at a rate of 100, like y is going up 100 for every one x goes over. That's why they call it exponential growth. It grows just as fast as its y value equals. It's crazy, but also really easy to remember. So that's a good thing. So just know that derivative of e to the x is equal to e to the x. All right, so we have our three new rules. Okay, what are they? Let's just recap really quick. Derivative of sine is cosine. All right, derivative of cosine is negative sine. Yes, that's going to be something you mess up all the time because it's so easy to mess up. So just really make a point of remembering. The derivative of sine is positive cosine. Derivative of cosine is negative sine. But then you have this easy one. Derivative of e to the x is e to the x. So these are our three new rules. So let's go ahead and use them. So in example 1, part A, notice we have this constant 2. So what we're going to use is called the constant multiple rule, which just as a quick little reminder in our little memory bubble, we learned this last video. If you take the derivative of a constant times a function, then the derivative of that would be that same constant times the derivative of whatever the function was. So in other words, the constant doesn't change when you take the derivative. It just gets carried down and is multiplied in front of the derivative. Okay, so we know that the derivative of sine is cosine, right? We just saw that worked out. So the derivative of sine is really truly cosine. So when I'm trying to take the derivative of f of x, which is a constant times sine, well then f prime of x would be that same constant times the derivative of sine, which is cosine. Nothing happened with the 2, basically. You just multiply it to the derivative of sine, which is cosine. Over here in B, we have a linear function times the trig function. So we have another derivative rule that we learned in our last video called the sum and difference rule. The sum and difference rule says, okay, if you're taking the derivative of the sum of two functions, so one function plus another function, then you basically just take the derivative separately and add them together. So we can think of x as like our f of x, we can think of cosine as our g of x, and take each of their derivatives separately and then add them together. So x is just a linear function. It's x to the first power. So the slope of it, which is the derivative, would just be, the derivative of it, which is just the slope, would be 1 in this case. But you could also think of that as using the power rule, because if we have the power rule that says if you're taking the derivative of x to some power, which in this case is 1, then you would bring that power in front and then subtract 1 from the power. So in this case, if I'm doing derivative of x to the first, I would bring the 1 in front and then I would subtract 1 from itself to get 0. But then x to the 0 is just 1. So you're just left with the number in front, right? Because it's linear. So with linear functions, I just think of it as just take the slope. The derivative is just the slope, which is whatever number's in front. So the derivative of x is just 1. So I'm going to call this y prime is equal to 1 plus the derivative of cosine. We just learned the derivative of cosine. The derivative of cosine is negative sine. So I just took the derivative of x separately was 1, derivative of cosine separately was negative sine, and then I just add them together. But since sine is negative, we'll think of it as subtracting. And there's our derivative. With part C, it would probably help to separate this out and think of it as 1/2 times sine of t. Because then you can think of it as a constant multiple. And we're going to use that constant multiple rule again, this one right here. That if you're taking the derivative of a constant times a function, the derivative is just that same constant times the derivative of that function. Again, we're going to use this fact too. Derivative of sine is cosine. So in this case, we're going to call it f prime of t, and it's just going to equal the constant times the derivative of sine, which is cosine. But we're going to say cosine of t just to stick consistent with the variables used here. And then again, in part D, we see a subtraction between two functions. So we're going to use the difference property of derivatives, which says that if you're taking the derivative of a difference between two functions, so f of x minus g of x, then you can take each derivative separately and subtract them. So that's what we're going to do here. We're going to do the derivative of cosine separately and then minus the derivative of pi over 3 times sine of k separately. Well, we know from earlier that the derivative of cosine is negative sine. And we also know that the derivative of sine is cosine. So here, derivative of cosine, that's going to be negative sine. So we'll say that h prime of k is negative sine. And then I also have a constant multiple rule, so we're going to be using that again. You just multiply the constant to the derivative. So I'm going to just do minus pi over 3 times cosine of k, since that's the derivative of sine. Let me just do a little simplifying here. So then I get negative sine k minus pi over 3 cosine of k. And that is our derivative for part D. How about you guys go ahead and try a few? pause your video here and come back and check your answers. All right, here are the answers I have for A through D. In A, we were using the constant multiple rule and just multiplying pi to the derivative of cosine, which is negative sine. So then the pi times -1 is just negative pi times sine x for our derivative. In B, we just used the power rule. So you bring the 5 down, multiply it to the 3 to get 15, and then subtract 1 from the power to get 4. So 15x to the 4th, and then plus 2 times the derivative of sine, which is cosine. So that derivative was, and I called it dy dx just to kind of show you the different notations again, right? dy dx and y prime are synonyms. And so it's 15x to the 4th plus 2 cosine x. For part C, I rewrote cosine t over 3 to just be 1/3 times cosine, so I could use the constant multiple rule. And so that was just 1/3 times the derivative of cosine, which is negative sine of t. Oh, I just noticed something. This should have been a t right here. Because we're taking the derivative with respect to t. I think I just accidentally called that x. That should have been a t. Sorry. So it should be 1/3 cosine t plus t squared. And so that derivative would be 1/3 times negative sine t plus 2t. Or negative 1/3 sine of t plus 2t. And then lastly, in part D, we have the variable theta. So it would be y prime is equal to the constant of pi over 2 times the derivative of sine, which is cosine theta, and then minus the constant 2 times the derivative of cosine, which is negative sine. Those negatives cancel, so we get pi over 2 cosine theta plus 2 sine theta. So let's try a few with our new function e to the x. So as a reminder, the derivative of e to the x is itself, so that'll be easy. So in this case, f prime is just the constant 3 times the derivative of e to the x, which is just e to the x. So in this case, the derivative equals the original function, even with the constant, because that's what the constant multiple rule says. You just carry it over to the derivative, and then derivative of e to the x is itself. So the derivative of 3 times e to the x would also be itself. Then here in part B, we're using the sum, taking the derivative of a sum. So we're going to do the derivative of x squared first, which is power rule. So we bring the 2 down, that's 2x to the first, plus the derivative of e to the x, which is just itself. So in this case, my derivative is just 2x plus e to the power of x. Why don't you try a couple? So we were mixing exponential and trig in these u-tries. So for A, again, we're using the constant multiple rule. So it's just 3/4 times the derivative of e to the x, which is itself. So the derivative of 3/4 e to the x is also itself, 3/4 e to the x. Derivative of 2 sine x would just be the constant 2 times the derivative of sine, which is cosine. So altogether, it's 3/4 e to the x plus 2 times cosine of x. Over here in B, again, we're using a constant multiple rule. 5 gets multiplied to the derivative of e to the t, which is just e to the t. And then add that to the derivative of cosine, which is negative sine. So altogether, you get s prime of t is equal to 5 e to the t minus sine of t. So example 3 wants us to go ahead and find the slope of the function at a given point. So we're going to find a numerical answer. And then we're going to also learn how to use the derivative feature on our calculator or graphing utility to confirm our results. So this will be a really nice tool to have handy. But the tool on your calculator only finds numerical derivatives at one particular point. So in this case, we're finding the derivative of g at pi. So we want to find g prime of pi because that would be the slope. That's the slope of the line tangent to g of t at the point pi comma 7, which is what it's asking us to find. So that's g prime of pi. But first I need to find g prime of t. So I do that using the rules we were just talking about. So I use the constant multiple rule, and so I take the constant of -2 and multiply it to the derivative of cosine, which is negative sine. And then I add that to the derivative of 5. So that's actually one rule we haven't reviewed yet. So that's the constant rule, derivative of a constant. not a constant times a function, but just a constant would be 0. Because if you could picture the graph of y equals c, it would be like a horizontal line. Y equals c. This is the x-axis, and that's the y-axis, and that's c. It's a horizontal line, and so the slope of that line is 0, right? Slope of any horizontal line is 0, and so the derivative is the slope. So the derivative of any constant is just 0, since it's the slope of a horizontal line. So then that, in this case, that constant is 5. So the derivative of 5 would just be 0. So g prime of t, it turns into just positive 2 sine t plus 0. So there's g prime of t. So now we can go ahead and find g prime of pi, because I can plug pi in for t. So that'd be 2 times sine of pi. So then we just have to remember what sine of pi is, what this value is. So it might help to think of the graph of sine. We've been doing that lately in our warm-ups. It starts at 0, goes up, comes to 0 again at pi, and then 0 again at 2 pi. So at pi, sine is 0. So actually g prime of pi turns out to be 0, because it was 2 times 0, which is 0. So the slope of the line tangent to this graph at this point is actually 0. It's a 0 slope. So what we're going to do right now is just confirm that with your graphing calculator. Let's go ahead and follow along with these steps.
Okay guys, so to check our numerical derivative, on our calculator we would actually go to this button right here, the one that says Math. If you click that, you're going to see a variety of options, but if you scroll down, you will see option 8, which is N derive. That stands for numerical derivative. That helps us find a derivative at a point, which is what we're checking right now. So you can either hit 8 or you can go down to 8 and hit enter. And then you should see this notation pop up here. So what you type in here would be the x that we're taking the derivative with respect to. So we don't want to use the alpha x, we want to use the variable x, which is this button here. And your calculator will automatically put that in as x. And then this is where you would type in the equation. So we were taking the derivative of negative 2 cosine x and then plus 5. Whoops, let me go back up here. And then plus 5. Sorry, had to add a parenthesis after the x because we don't want to add 5 inside of cosine. That would be wrong. Also notice that I'm using x instead of t because that's what your calculator understands as the variable. And then x is automatically right here, and then you just type in pi because that's what we're taking the derivative with respect to. So I have to hit second and then pi, and then enter, and it should go ahead and give you the derivative, which is 0, which is what we got. So then that helps us know that we got it right. So it's a great way to check your derivatives. Also, one thing too, really quick, if you are doing derivatives or integrals with trig functions, you want to make sure you're in radian mode, not degree mode. Maybe I'll just kind of show you how, if I had done this in degree mode, so let's do it, then I might have gotten the wrong answer. Yeah, so like it would give me 0.001913, which I guess if I rounded would be 0, so maybe you'd be safe, but sometimes it's like way off. So always make sure you're in radian mode when you're using numerical derivative tool and trig functions, so we can get our clean derivative of 0.
How about you try one? Okay, so when we find the slope of the graph of the function in this example at 1, well, so we wanted to find f prime of 1, we had to start with f prime of x first. So f prime of x would just be the constant of negative 4 times e to the x, times the derivative of e to the x, which is e to the x. So actually f prime equals f in this case. So then the derivative of f at 1 would equal negative 4 times e to the first power, which equals negative 4e. So remember what I was saying earlier. The slope of the tangent line, that's this guy, right? Slope, or the slope of the graph, right? Slope of the tangent line, slope of the graph, equals the y-coordinate of the tangent line. So it's growing at the same rate as its actual value. Pretty crazy. And then this is what that would be in decimal form. I just write that down so you can that can help with verifying with your calculator. So let's go ahead and do that now.
Okay, so let's walk through this numerical derivative check one more time with the U-try. So you go to Math to access the numerical derivative tool. It's option 8. So I'm going to show you, I'm just going to click 8 because 8 will just tell it to use the 8th option, which is in derive. I'm going to type in x for what I'm taking the derivative with respect to, x of my equation, which was 4 times e to the x. So I'm going to use this one here, the one that's right above ln. So I'm going to hit second, e to the x. And I'm taking the derivative again with respect to 1. So this is, or sorry, at 1, at x equals 1. So this little line here means I'm going to evaluate the derivative. So it's going to find the derivative and then evaluate it when x is equal to 1. That's kind of what that means. And so we'll hit enter. Oops, I'm sorry. I realize now this is supposed to be -4. Sorry, let me go back. Boop, 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 boop. And I'm going to do second, insert, and I'm going to type in a negative sign, not a subtraction because it doesn't understand that that's negative. Okay, and then now I'll hit enter. So there we go. There's that decimal that we know was equal to, because we did that earlier, it was -4 times e to the power of 1. If we type that in, we see, oh, that's -10.873127131. So we got that same value here when we were taking the derivative of this function evaluated at 1.
And that concludes this video. Thanks for tuning in. See you in class.